All right. So let's begin. So today we will focus our attention on dynamic programming, and we started looking at this problem, longest common subsequence. We will solve that, and then we will try to put together a recipe as to how we go about solving dynamic programming problems. Then we will do one more example. This is a weighted version of interval scheduling that we did, that we covered early on with greedy algorithms, and then we will, if we have time, we will define this commonly occurring problem called the knapsack problem. So this will basically introduce to you the technique of dynamic programming, and we will go on to give more examples, and we'll do a lot more problems in the coming class. Reminder that quiz 3 is on Friday in class, and this will be covering greedy algorithms and parameters. Okay, so recall what the longest common subsequence problem was. I'm going to write it as LCS. You're given two sequences. X and Y. Find longest common subsequence of X and Y. Okay? And So last time we observed that if you look at the sequence x and y, and you have some characters, put those two to that. If you have these two sequences, and we want to find the longest common subsequence of both of them, one thing we observed was if the first character just happened to be exactly the same, then intuitively it seems like we should go ahead and match them. Okay. And so that suggests that, oh, there might be sort of some kind of a greedy approach where if I do find a match, I will go ahead and match them. Okay. So that's a reasonable idea. We can try to see how we can push that. But then once you decide to match them, we come across A and C, which are not a match. And now we don't know what to do. Do we take A or do we take C? A matches with this A, this C matches with this C, and we know that we can only take one of the two. Okay? So, while sometimes there is this greedy choice that seems to work, some other times it's not clear whether there is a greedy choice that will enable me to push this. So, and we don't have the luxury of trying both of those then. So, we could say, okay, I'm going to try A, and then I'm going to try C, and then I will try both of them separately. But when I try A, then I have to move like this. And then again there might be two choices. And then there again might be two choices. And this could lead to an exponential running time because you might have two choices at sort of every point. Okay. So let's try to see how we deal with that situation. So fundamentally what's going on is we are trying to see that there are two cases. One case is when they are the same, and the other case is when they are different, and then when they are different we have to try to do something. Okay, so the first thing in dynamic programming is to see whether there is something like an optimal substructure. Okay. Which enables us to say something about the fact that if a solution is optimal, then it contains optimal solutions to subproblems. Okay. What is the optimal substructure with an optimal solution? Contains for subproblems. Like in a greedy algorithm, we pick the first choice or some particular choice, and then we say, oh, the remaining problem is the same as solving the optimal problem for finding the best choice for the remaining part of the problem. Right? So you take a choice, and then the remaining problem is of the same kind. Here also that kind of question comes up. Is it there? Can I break the solution down, optimal solution down, into a piece that I have to find out whether it belongs or not, and then the remaining piece that is an optimal solution for the subproblem? Okay. So let's try to be very concrete in this context. So what I'm going to do is we are going to compare characters. It's actually more convenient to compare characters at the end, and you'll see why it's a little bit more convenient just in writing the algorithm. So I'm going to compare the ends first. You agree that whether we start from the left or the right, it doesn't matter. It's the same procedure, right? Okay. So let's try to see. So I'm going to do a check. Let's check to see whether xm is the same as yn. Okay? So look at the last two characters and see whether they are the same. So if they are the same, then we would like to claim that, oh, if they are the same, we should just take both of them, the characters in our solution. Okay? And then what would be the remaining problem? So let's take an example where they are the same. So this is T and T. Okay? So these two characters are the same. So in this case, I would like to say, oh, my last character is going to be G. Then what would be the remaining problem? The rest, where you're comparing x from 1 to m minus 1 to y from 1 to n minus 1. Okay? So if xm equals yn, then I want to say that, oh, the longest common subsequence for x and y is the same as from x1 to m, y1 to n is the same as LCS for x1 to n minus 1, y1 to n minus 1, followed by the last character, xm. Okay, this is just the append notation. Okay, just put in the D. It's followed by xm. Okay, and this is, by the way, very cumbersome the way it's written. We'll make it very simple in a moment, but you're getting the idea that if these two characters are the same, then the LCS of the pair of sequences is the same as the LCS of the pair of sequences of the last character move, followed by xm. What if they are not the same? Okay. So in this case, let's go back to our example here. The C is not the same as G. Okay? We know that, so at this point, we have no idea whether C is part of, whether we should include C or G. But the only thing we know is we cannot include both of them. Right? You see, I cannot match C and G. Okay? So the point is, either I'll have to eliminate G and find the longest common subsequence of these two, or eliminate C and find the last common subsequence. The last character cannot be both C and G. It has to be one of them. It may be neither of them, but it cannot be both C and G. So if xm is not equal to yn, I can say that LCS is either LCS of x and y, where I remove the C, so 1 through m minus 1 and then 1 through m, or 1 through m and y 1 through n. It's either one of them. It cannot be both. Which of these will you choose? The larger of the two, because you're trying to maximize the thing. So we can replace this, right? Okay. So let's make this cleaner. So actually, before we make this cleaner, let's try to argue that we are doing the right thing. Okay, so this is not a complete, this has not been clearly fleshed out as an algorithm, but let's try to agree that these statements we are making are correct. So proof of correctness. If xm equals ym, we want to prove that the LCS of this is the same as LCS of this followed by xm. Okay? So we are in a situation where this last character is the same for both the sequences. This character is the same. We want to prove that the LCS of this is the same as LCS for of the two things we've written here, followed by alpha. Okay. How do you prove it? Suppose not. Suppose op is different. Okay. So we have given, we pick the sequence that looks like this. It picks something here. It picks something here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then alpha. But let's say op did something else. So we'll ask the question: did op pick alpha? Does his last character of op alpha? If yes, then op minus its last character is a common subsequence of x 1 through n minus 1 and y 1 through n minus 1. Right? If it does include alpha, then when you remove that alpha from op, when you op looks like some bunch of characters followed by alpha. So if that does include alpha, then when you take out the alpha, whatever remains has to be in here and in here. So it's a common subsequence of these two. While we are picking LCS of x n minus 1 n minus 1. Okay, so if op is different, then this is a common sequence of x1 minus 1. And we are selecting the longest common sequence of minus 1. So essentially what is going on is this is a proof by induction. Okay? Let's assume that we have found the LCS correctly for smaller things, then if this is LCS, if this is LCS, if this is LCS, then LCS for x1 through m and y1 through m is defined as these two. Okay, let's complete this. If xm was not the same as yn, so the last two characters are different. This is alpha and this is beta. Then the optimal solution we are claiming either includes alpha or includes beta or includes neither. If it does not include alpha, then whatever you pick has to be a longest common subsequence of this and this. Right? If it does not include beta, whatever you pick has to be a longest common subsequence of this and this. And in our solution, we are taking the max of that. And so this indeed would be the longest common subsequence. X 1 through m. Okay. So what I'm going to do is write this in a more succinct manner, which will help us better. And I'll write down a recipe as to how we go about doing this. And ultimately, what I will point out is this is what is called a recurrence. This recurrence is essentially the entire algorithm. That's all we'll be thinking about. Okay? And once you get a handle on this, you'll basically solve this problem. We will do the same thing for two of the other problems, and you'll see how the whole. And I'll also show you an example for okay. So okay. So what we will do is, often when we are dealing with, yes?
What if alpha is not the last character of our op?
If alpha is not in the first case or the second case?
In the first case.
Well, in the first case, essentially we'll say the last, good. I should have taken that too. Let's say alpha is not the last character of opt. Then you agree that opt, if you remove alpha, opt is a subsequence of both of them. Okay, because alpha doesn't even appear there, so if you remove. But then that means to opt, you can add alpha and increase opt.
But what if the next, we are moving from the right side, and if the last character is the same, but not the next one after that?
Correct. So the point is that let's. Okay. So let this whole sequence be W. Let this whole sequence be Z. Okay. So suppose opt last character opt is not equal to both. Okay. Then opt is the common subsequence. So common subsequence of W and Z. Every consider opt followed by alpha. Okay. So opt occurs here, and then let's say I add alpha. Opt also occurs here, and then I add alpha. Then you agree that opt followed by alpha is a common subsequence of x and y. But what is the length of opt followed by alpha? It's opt plus 1. So that's a computation. Okay. Okay, so all of the questions we will be looking at, okay, will be of the form, there will be an associated objective. Okay. What is the objective here? The length of the sequence. In weighted interval scheduling, the objective would be the sum of the weights of the intervals that we select. Knapsack, there's another problem, the objective function would be the sum of the value of the objects that we select. Okay? So all of these have some objective in mind. But what you want to find is a solution that has the highest objective. Like minimum spanning trees, you want to find a spanning tree that has the least weight. Okay? So all of these will have an objective, and all of these will have a kind of a solution, which will be a tree or a set or whatever. So what is often is convenient is to separate the two. So let me define that here. So let me say LCS of I is optimal longest common subsequence of x 1 through I and y 1 through j. Okay? LCS ij. Let me define this to be the longest common subsequence of x 1 through I and y 1 through j. Okay? So notice the notation. I'm changing the notation from here so that I'm not putting x and y inside. So I'm making it simpler, just easier to handle. So let me define LCS ij to be the longest common subsequence of x 1 through I and y 1 through j. Okay. Let me also use a particular thing called L ij. This is the length of LCS ij. Okay, it is often very convenient to work with the length as opposed to the actual sequence, because what you're really comparing is the length. Okay? Are these two definitions clear? Okay? Okay, good. So now I can go ahead and write that recurrence in terms of L. Okay? And let me write that in the middle. So L ij equals, if we find that the last two characters are the same, then it's simply one more. We are just adding that character to our solution. Okay. Xi equals yj. You agree? What if xi is not equal to yj? What is Lij? It is the max of two quantities. What are the two quantities? L of I j minus 1 and L of I minus 1. Okay, all I've done is rewrite that in this form entirely in terms of lengths. Okay? Is it clear? Ah, it's the maximum. Let me. It's maximum of L I j minus 1 and L I minus 1j. Okay, here the condition is xi equals yj. Here the condition is xi not equal. Okay? Okay. So this looks good. So you clearly see that there is a recurrence of how you're defining Lij, how you're solving Lij by solving Li minus 1j minus 1 or ij minus 1 or I minus 1j. Okay. One, of course, issue with recurrences always is you need to have a base case. So what do you think is the base case here? So this is going to continually decrease, j is going to decrease, I is going to decrease. So the base case would be when either of them becomes 0. So what will be the case if one of the strings is empty? What is the length of the longest common subsequence? 0, right? If one of the strings is empty. So this is equal to 0 if either I equal to 0 or j equal to 0. Okay? These two assume that I and j are both greater than 0. Okay? Good. So, I'm spending a fair amount of time developing this recurrence because I want to emphasize that this is the heart of the algorithm. And you will see that we'll go over a couple of things as to why this is the heart of the algorithm. It's not obvious at this point what is the running time of the algorithm or anything like that, but it will soon become very clear how to take such a thing and translate it into an efficient algorithm. Okay. So notice that this is a recurrence, right? And what do we use recurrence often for? For analyzing recursive procedures, right? And in fact, a recurrence corresponds to a recursion. So you can translate this into a recursive algorithm. In fact, this is exactly, you can see that it's a recursive algorithm. I can write it out immediately. It has two inputs, I and j. And you first put the base case. If I equal to 0 or j equal to 0, what do? You return 0. Now we are in this case where both of them are greater than 0. So now what do? You check if xi equals yj, what do you return? 1 plus L I minus 1 j minus 1. Otherwise, what do you return? The max of the two. That's it. That's the same. You can translate that as an algorithm. There is a problem with this. And the problem is the following. So let's think about, let's unravel this and see what goes on. Let's say you're trying to find LCS for two sequences, one of length 8 and the other of length 5. Okay? So let me draw this node indicating that you're looking at this problem where there is 8 characters on one and 5 on the other. You're going to check whether the last characters are the same. So there are two possibilities. equal to or not equal to. If it's equal to, what is the problem reduced to? 7 and 4. If it's not equal to, what is the problem reduced to? Well, so now you have to take a max of two things, which is 8 and 4 and 7 and 5. So this only you have to do only one of them. Either you do this or you do this, right? You don't have to do both. But here you do have to do both. Okay? So this is an and. You have to do this and you have to do this. Okay? Let's keep going. If you encounter 8, 4, what do? You check whether they are the same. Let's look at the case where they are not the same. Then what happens? You solve for 8 and 3 and 7 and 4. So you do and. If it's 7, 5, again there are two cases. So 7 and 4, 6 and 5. Okay? And this is an and. And there is an or here. Okay. So every time if you look at the not equal to thing, there are two children, right? So if this has, let's say both pair of let's say both of these are of size n, then this will go down to n minus 1, this will go down to n minus 2. So how many children, how many nodes did you have as you grow down? 2 to the power of something like 2 to the power of n. Okay. So indeed, if you were to run this code as this is an exponential time algorithm. Okay. And it's essentially the same as checking all possible subsequences. There is no difference between this and checking all possible subsequences. But it turns out there is a clear silver lining, and the silver lining is in the following. You see here in this example that the 7-4 is appearing twice. Okay? What does it mean? What it means is then this is whatever you're doing below this is exactly the same as whatever you're doing below this. They're exactly the same problem. So the question is, why should we do both? Why don't we just do one of them and reuse it when we need it? Okay? And that is the hallmark of dynamic programming, that you have a lot. If you were to do it recursively, you would have an exponential size. But it turns out that in reality, the sub-problems overlap. And you can dramatically reduce the amount of time it takes. Okay? So to understand that, how many different possible inputs are there for this function? How many choices of I are there? N. How many choices of j are there? N. So the total number of possibilities of the call to L is only m times n. So even though there are an exponential number of calls, if you were to do it this way, the total number of different computations we are doing is only m times n. Okay? So there are two ways to deal with it. In my opinion, the easiest way to think about it is just instead of writing a recursive procedure, we will write an iterative procedure. There's a different way of doing it, is to do this as a recursive procedure, but before we make the recursive call, we will check to see whether we have already done it before. If we have done it before, we won't do it again. Okay? and that's what's called memoization. So there are two ways to do this. Both of them are equivalent and they work exactly the same way. It's the same, take the same amount of time, but there are two ways to do it. So let me present to you the iterative procedure first. And okay, so the iterative procedure is going to look like here. So this is for Lij. So okay, for Lmn, I'm going to compute Lmn. This will be going to find the length of the longest common subsequence of x1 through m and y1 through n. What do? First, you make sure that first you take care of the base case. For I going from 1 to m, you set L I0 to be 0. For j going from 1 to n, you set L0j to be 0. Okay. Actually, maybe you should take 0 as well. I going from 0. Okay, so that's the base case. And then you check for I going from 1 to n, for j going from 1 to n. If xi equals yj, then Lij equals 1 plus Li minus 1j minus 1. Else Lij equals max of Li minus 1j. And then you return L and okay. So all this piece of pseudocode has done has translated this recurrence and written it in the form of code. Okay? It has taken this recurrence and provided an order in which you have to execute this recurrence. And it's obviously ordered, right? Before you can do ij, you must make sure that you have done I minus 1, j minus 1. You must make sure that you have done I, j minus 1. You must make sure that you have done I minus 1, j, and so on. Okay? So, we wrote the recurrence down, and we take the recurrence and write it as a piece of pseudocode. We can take the same recurrence and write it in this recursive form. That's also perfectly fine, except that here we have to add these memoization things, where we have to say, instead you check if this has already been computed, then you don't make the call again. You just refer to the value that you're stored somewhere. Similarly, you don't make these two calls if you've already computed them before. Okay? Any questions at this point? Yes?
If we're starting from the back of the array,
Yeah.
the loop there, I don't know if I'm misunderstanding the pseudocode. Why is it 1 and why would it be 10 down to 1?
So we don't, so you could start whichever direction you want to go. You can do it. Here, let's see, so the way to think about it, we are not the way we have written the recurrence, it's not like we have started from the back of the array. We basically, if you make so think about the recursive call is a top-down procedure. So that would, you will make the call to lmn. The first thing it will check is xn equals yn. That's a top-down. Okay, so it'll look at the top xn equals yn, and then it'll make the lower calls. An iterative procedure is bottom up, because before it can do lmn, it wants to make sure that it has done everything else before, right? So it starts from I1 to m, and then 1, so that by the time you reach m and n, you have done all of the i's less than m and all the j's less than m. Okay. So these are two. They're exactly the same thing, but they're just two different ways of looking at it, whether you're doing it top down or bottom up. Okay. Yes.
So when we return L of m comma n, we are just returning the max length, right? We are not actually returning.
Correct. Yes. So we'll talk about that in a moment. Any other questions? So the question here was that we are just returning the maximum value. We are not actually returning the sequence, and that's correct. The way we have written it, we are not returning the sequence. Okay. Any other questions? Okay. So but I wanted to do it in a sequence of steps like this, because we will be doing this again and again. Okay. We'll be writing the recurrence. Then we will be translating that into pseudocode, either this way with memoization, or this way where I have provided more details. The next step we will try to add to it is get the actual sequence. Sometimes you don't have to go through these steps. You can directly get this sequence if you want. So if I had to adjust this recurrence so as to get the actual sequence, what can I do? Okay, and there are, depending upon the problem, you can do different things, and it's convenient to do things for a specific problem. So let's go through an example, and we'll see exactly how we will convert that into extracting the sequence. Okay. So let's take an example, and let me take an example from CLRS on the textbooks. So let's say we have two sequences. Let's say X is algorithm and Y is altruistic. We want to find the longest common subsequence between these two sequences. Okay. Remember, what we are really trying to do is calculate the length of these sequences. So we have an array. Okay. So let's build this array. Actually, maybe I'll need more space. Okay, so I'm going to write down here. So X is algorithm. So X 1, 2. So it will go like this. So this is A, L, G, O, R, I, T, H, and other one is altruistic, so it's A, L, C, R, Q, I, S, T, R, C. So R, U, I, okay. Okay. So this is 1 through n. This is 1 through n. Let's just follow what we are doing there. Exactly. So the only thing it doesn't show is 0, 0, the 0 array. So imagine there is an array here, a row, a column here, which is all zeros, and imagine there is a column, a row here that is all zeros. Okay, that's not being shown. So it's all zeros above here, all zeros below. Okay, so let's go with this. I going from 1 to m, j going from 1 to m. So we start with I equals 1, j equals 1. So we check, is xi equals yj? Yes. So if xi equals yj, then what is L of ij? Well, it is L of I minus 1, j minus 1 plus 1. That means we're going to look at the diagonal entry here and add 1 to it. What is the diagonal entry here? 0. I told you that column there. So it's 0 plus 1. Okay? When you compare, now let's say I equals 1, j equals 2. So I equals 1, j equals 2. Now what do? We compare A and L. Are they the same? No. So you take the max of the above entry and the entry to the left. Okay, which is 1. A and T, are they the same? No. So take the max of this and this, which is 1. 1, 1, 1, 1, 1, 1. Okay? But again, we are only calculating the length. How do we keep track of where we are getting whether there is a match or not? So this one corresponded to a match. So remember, if the last character matched, then what do? We subtract 1, right? That means we say that the remaining problem is the problem that is in the diagonal entry. So what we will do is whenever we see a match, we will add an arrow like this. Okay, I'm adding a new field here, which indicates what is the remaining problem. Okay. Here we took the better of 1 and 0, which is 1. That means we are saying that it's better to solve this problem than to this problem. So I'm going to draw an arrow here. Okay. So what I'm doing here is, I'll just make an update to that code in a minute, but you'll see what is going on very shortly. So A and L, are they matching? No. So I take the maximum of this and this, and this is a 0. So I get 1, and I put another arrow like this. Okay. A and G, 1, arrow like this. A and O, 1, arrow like this. A and R, 1, arrow like this. 1. Okay. Now things will become more interesting. So I'm going to fill in column by column, right? L and L, do they match? Yes. So I take the diagonal entry and add 1 to it. So I got 2, and I add the diagonal. L and T do not match, so I take the maximum of 2 and 1, which is 2, and then I put an arrow above. Okay. 2 and 1, sorry, L and R does not match, L and U does not match, L and G does not match. I take the maximum of these two. G and T does not match maximum of these two. It doesn't matter which one I take. I can do this. R and G, G and U, G and I. Okay, L and O. Okay, L and R. So everything here, L does not match with anything, so all of these would be this. T matches with T matches with, so T does not match, so let's do this. So R matches with this R, right? So we'll do this. R matches with this R, so we get 3 and a diagonal. Okay. So I'm going to fill this in just so that we complete this. And so U, R does not match with U, so it will be 3 up. 3 up. Okay. I does not match with this, so I does not match with R. U does not match with I. I matches with I, so I get 4. Diagonal. S does not match with I. 4. Oh,
I matches with that.
I matches with I matches with I, but we don't see a I, so I get 2, 4. Okay. T and T, they do match. 3. T and T, they do match. R and T, they do not match. T until this point 4. S. Okay. T, they do match. T and T, so 5. I does not match. Okay. H does not match with anything, right? And M does not match with anything. So it'll just take the maximum. Okay, alright, so this was quite tedious, but the value of doing this exercise is we are basically running this piece of code, except that we are adding this one marker which enables us to figure out, keep track of the case that gave us the solution. And now, in order to find the LCS of M and N, all we need to do is we will follow the arrows. Okay, so we will start with from the very end, and this number will give us the length of the maximum common subsequence. That's 5. And this says go left. That means this is not a match. So we'll go here. This says go up, so it's not a match. Go here. This says go up, so it's not a match. Go here. This says go left, and we see an arrow diagonal. That means this is a match. And what is that match? T and T. So the last character is T. That matches. Here. From here we'll go to here. 4, this says go up. 4 diagonal, that's a match. I and I. So the last character is previous match. The next match is I. So it goes here. Up. That's another match. R. You are here, right? Then it goes here. It goes here. It goes up. This is a match. L. That's a match. So this is the longest common subsequence. Okay. So one way to adjust this is we will make a note if Lij is 1 plus Li minus. If it's this case, then we will have another array that will keep track of these arrows. Okay, let's call that array, I don't know, capital M. So we will say Mij is this arrow. Okay, and if it's one of these two cases, then if this was the max, then we will go I minus 1. I minus 1 will be left. If it's this the max, then we will go j minus 1, which will be up. Okay, so in this situation, Mij will be left. In this situation, okay. This is not the only way to do it, but this is just one way to do it. Typically, I think going from this recurrence and being able to extract the actual solution as opposed to the cost is some work, but it's sort of more routine work. You just have to keep track of things. This is really the crux of the problem. Okay? So let's try to understand the different pieces of this. So the first piece is being able to write a recurrence. And the recurrence captures something called the optimal substructure property. Okay, so you have to understand what the optimal solution looks like. You try to identify an optimal substructure property. From that you capture a recurrence. Essentially the recurrence is its own proof, but you should be able to make the argument like we made a proof of correctness argument there as to why this recurrence is correct. Once you have the recurrence, you should be able to either translate it to a recursive algorithm using memoization or an iterative algorithm using just for loops. Okay? Which will tell you in what order you should do the recurrence. Once you have done that, you should be able to say, okay, how can I make changes to this to include ways to actually recover the solution as opposed to just the cost. Yes?
So I guess the letters that you identified there, neither words that occur sequential, the algorithm.
Yes, so subsequence means not contiguous. Subsequence, that's a different problem. You could ask, I want two things that are contiguously, those are typically referred to as substrings. That would be the longest common substring problem. The longest common subsequence problem is, I want two subsequences where I do not need contiguity. I can drop things, but they have to appear in the same order. Okay? So ALRIT appear in the same order. Here, ALRIT appear in the same order, but they are not contiguous. Yeah?
Is it that if we do recursion, we start from the last? So we follow only what is needed? Because for
No,
iterative, we are filling up everything.
they are the same thing.
That's what we-
Yes, you will be doing exactly the same thing in the recursive call as well. You have a question? Any other questions? Okay. Good. So let's do a couple of other problems. We won't be going through every single step of those problems. Yes.
Can you repeat what it is, what you do, the recursive algorithm to make it?
Oh, to manualize? Okay, good. Okay, so this is an exponential algorithm. If you had to use memoization, what would you do? Okay, so what you would do is let me write this out here. You would so you define your thing like this. The first part is the same. If I equal to 0 or j equal to 0, term 0. Okay? If xi equals yj, okay, you are maintaining a global array let me call that, just so that there is no confusion, let me call that array L star you're maintaining a global array that keeps track of what all you have computed so far. Okay? Initially it is set to so actually let me do one thing. Just one second. So if I equal to 0, right, if I equal to 0, then you say L star ij equal to 0 and you return 0. Okay? So while you are calculating this, you also fill the same table that we are filling there, we fill it. Why do we fill it? Because if we see that the table has already been filled, we don't want to go back and recompute it. Okay? So if I equal to 0, you set L star ij equal to 0 and you return 0. If j equal to 0, you set L star ij equal to 0 and you again return 0. I could have written it the same way before, but that's okay. Otherwise, you're checking if xi equals yj. Okay. Initially, you set every entry in L star to be something not defined. Okay. Some null, let's say. Okay. Or -1 or something. So if xi equals yj, then you would like to return 1 plus li minus 1 j minus 1. But you check whether li minus 1 j minus 1 has already been done before. How do you check? You look up L star. Okay. If L star I minus 1 j minus 1 is not equal to null, okay, if L star I minus 1 j minus 1 is not equal to null, okay, so if L star I minus 1 j minus 1 is not equal to null, then you go ahead and use the value already there. Then you set L star ij equals L star I minus 1 j minus 1 plus 1 and you return that. Okay, I'm realizing as I'm writing this, I'm making it more complicated. And we will discuss how there is actually a much simpler way to do it. But let's do this for now. Okay, so is this clear? So if xi equals yj, I check L star I minus 1 j minus 1 is not equal to null. If it's not, then L star ij equals this plus 1, and then you return L star ij. And you do exactly the same thing here. If xi not equal to yj, then you look at, so I'm not rewriting that, you look at this, remember what were these two quantities? These two quantities were L I minus 1j and L ij minus 1. Let me finish this. So L star I minus 1j minus 1 is not equal to null, then you change L star ij, return L star ij, else you're going to make the call. L star ij equals L I minus 1j minus 1. Notice that this is the recursive call. You're setting L star ij to be a call to L I minus 1j minus 1 plus 1, and then you return L star and so this is for this case, we'll have to do something very similar to this case. Okay. Again, what are we doing? Before we make the recursive call, we do a check. Has it already been done? If it's already been done, we simply look at the table. Okay. Right? Now this could have been written a little simply by doing this check only at the beginning. Okay, so when you make the recursive call, then you look up your table. Have you already done this? If you have done this, you just return from the table. If you have not done this, then you go ahead and make the recursive call. So let me see whether I can write that out here. L star ij is not equal to null, return L star ij. Okay? If L star ij is not equal to null, you simply return L star ij. So that's what, you just check. Have you done it before? If you've done it before, you simply return it. Otherwise, you're going to do the call. Otherwise, what do you do? If I equal to 0 or j equal to 0, set L star ij equal to 0 and return L star ij. If else okay, I'm going to do just one case and then we'll read it. Third is if xi equals yj. If xi equals yj, what do? You do L star ij equals L I minus 1 j minus 1 plus 1, and then you return okay, I'm only writing one case. So in this case, the check for null is you only do it at the beginning. Alright, so let's go on. So now, going forward, we won't be...
Professor?
Just one second, sorry. I'll leave this here. Okay, so let's take the next problem, weighted interval scheduling. Okay, the weighted interval scheduling problem is the same as the interval scheduling problem, except for the fact that you have now weights on the intervals. Okay, so imagine it's like scheduling these intervals or scheduling these lectures in a location, but now you're getting different dollar amounts for different lectures. So you are supposed to maximize your revenue. So you're given a whole bunch of intervals. Okay, this interval is of value 2. This is not the length of the interval. This is the value of the interval. Okay, the weight of the interval. This interval is value 5. This interval is value 1. This interval is value 3. 2, 9, 4, 3, 2. Okay, so you have a bunch of weights, and your goal is to find the maximum weight collection of non-overlapping intervals. Okay, is the problem clear? Again, you have to find a set of non-overlapping intervals. In the past, we wanted to find the set of overlapping intervals that has the largest size. Here, we have to find the set of overlapping intervals that has the largest weight. Okay? So, when you're facing a problem like this, we can try to apply the same greedy choice method that we had before. We could find the interval that finishes the earliest. The problem with that is if that's completely oblivious to weight, clearly that's not going to work correctly, right? So for example, here, if you pick this interval of length whose weight is 2, which finishes first, you are eliminating the possibility of picking this interval, which clearly seems to be more valuable. Okay? You could instead go with the thing, okay, I'm going to pick the largest weight interval. You can easily come up with an example that that's not going to work either. If you're always going to pick the largest weight interval, you might have an interval of weight 5, but then 2 intervals of weight 3 each, and you are, by picking this, you're eliminating these 2. Okay? So it does not take that much time to recognize that it's almost impossible to identify one interval for sure that we are going to pick, and by just making a few checks like this. Okay? So the idea of the algorithm is essentially what we will do is we don't know whether, in the same way that we do not know whether we want to pick this character or not in our longest common subsequence, we do not know whether this interval that finished first should we pick it or not. Okay? So suppose we sort the intervals in order of their finish time, in increasing order finish time. Okay? So let's suppose I write down the intervals in increasing order of the finish time, and let's say these intervals now are I1, I2, I3, In. Okay? So these are n intervals, all sorted in finish time. So the finish time for I1 is before the finish time for I2, which is before the finish time for I3. Okay? Okay, So I sorted them. Now I ask my question, should the first interval be part of the optimal solution? Okay? And as I said, we don't know whether it should be part of the optimal solution. Okay? So, as in this case, we do not know whether the first interval should be part of the optimal solution, but there are two possibilities. Either it is part of the optimal solution or it is not. Okay? So let me, so let's consider here this interval. Is it part of the optimal solution? We don't know. Possibly is not because of the 5 sticking there, but we don't know. If it is part of the optimal solution, then what is the remaining problem? So the remaining problem consists of all intervals that begin after this point. Actually, I should draw it correctly, but they begin after. You agree that there is no other thing to do. If somebody told you for sure this is part of the optimal solution, your remaining problem is now everything that starts after this. Okay? If I told you that this is not part of the solution, optimal solution, then what is the remaining problem? Everything minus that. Because you know that this is not part of the optimal solution, so I can ignore it. So you realize that what is happening is we are giving two possible subproblems. One just ignoring one, and the other just ignoring some prefix. Okay? And that's exactly what will give rise to our recurrence. Okay? So I'm going to write a recurrence for this. For convenience, again, I'm going to, instead of asking the question about I1, I'm going to ask the question about IN, because it allows us to write the recurrence more easily, but it's the same thing. Okay? Okay, let's see. Okay, so so let's call, let me W, let's say Wij is equal to the weight of optimal solution for the problem consisting of intervals. Oh, I'm using, imagine the intervals were I1, capital I, capital I2, capital I3. Okay. I use the small i's, let me use capital I. Okay. So imagine the intervals are capital I1, capital I2, capital IN. So weight Ij is the weight of the optimal solution for the problem consisting of intervals I through j. Okay. See, we don't need to be so complex. It might be easier. Let me make it easier. Theta j. So weight Wj is the weight of the optimal solution for a problem consisting of the intervals I1, I2 through Ij. Okay, I want to solve this problem. I want to solve all the intervals, but instead, so I'm going to write this recurrence down. Weight of j. Again, we'll start with the base case. What is the base case? When j is 1, there is only one interval. If there is only one interval, what's the optimal solution? You pick that interval. So it's simply the weight of that interval. Yeah. J equals. Okay? Clear? Otherwise, so now j is greater than 1. Remember, we are looking for the optimal solution from I1 through Ij. So we are looking at this interval that finishes at the very end. This is the one that is finishing at the very end. So we are asking, should we take it or not? If we decide to take it, what's the remaining problem? All intervals that end before j begins. Right? So all intervals that end before j begins. So, well, there is, you agree that there is a k, so let k be the largest value such that the finish time of the interval k is before the start time of interval j. Anything after k is not valid, right? Because anything after k finishes after that point where the first one starts. So that's k. So my remaining problem is, of course, I'm including j, right? So I'm including j, whose weight is wij. Then my remaining problem is wk. I'm including the interval j, and my remaining problem is wk. Because what is k? K is the largest value such that f of ik is less than or equal to Sij. If I decide not to include ij, then what's my remaining problem? W of k. No? J minus 1. So there are two possibilities. What do I do? Take the max of the two. I do not know which of these two possibilities is the right one, but I simply can take the max of the two. Okay? Remember, this k is defined here. Where k is the largest value, so that f of ik is less than or equal to Sij. Okay? Again, I want to emphasize that this is the heart of the algorithm. Essentially, if you have written this recurrence down, you're done. Okay? It's good to know how to translate this to code. It's good to know how to extract from that the solution. Notice that here I'm only keeping track of the total weights, but it's very easy to extract the solution, right? If I did this, then I will make sure that whenever I do this, if this is the maximum, then I will make sure that I will not keep ij. If this is the maximum, then I will include ij in my solution. Okay? But this gives you the crux of the. I'll make two comments that I did not make before. So one was in our algorithm, I forgot to analyze the running time. Remember, there were two for loops in that. One was running for n steps and the other was running for m steps. So the running time of that algorithm was simply n times n. Okay, so this is simply n. The running time of this algorithm is every time j is decreasing by 1 and you are taking just the max of two things. So the running time of this algorithm you will see will be simply linear. Once you have sorted all the ij's, it will be simply linear. If you need to take into account the time for sorting, that's n log n plus 6. Any questions? Yes.
Can you say that because you are making the assumption that I'm going to start from the end,
Yeah.
then you can write max.
Yes. So we have to sort. Oh, so sorry. What's the question again? So,
Like, you're saying that it's easier for me to start from behind and then.
so that is just a convenient way to write it, but it's not a big deal. You could have written down exactly the same thing going this way. It's just that how you define this. Wj is the weight of the optimal solution for a problem consisting of intervals I1 through ij. If you were doing it in this direction, then the problems are not of the form I1 through ij. The problems are of the form ij through in. Because you're taking things from this side, right? So then you can write exactly the same recurrence, but then you will be essentially a similar recurrence, but then you will redefine your Wj as then in that case, let me write as W prime j. W prime j would be the weight of optimal solution for subproblem consisting of instances consisting of intervals ij plus 1 I. Okay, because you are taking things from here, so the remaining problem is the suffix. Okay, if you are taking from the end, then the remaining problem are the prefixes.
The max condition still holds true.
The max will still exactly the same thing will hold, because where is the max coming from? This problem is asking you to build the largest weight. That's why the max is coming. The question is asking you to find the largest weight solution. So that's how the max is coming. Okay. So I have your quiz that I will return. I didn't want to make a comment about the quiz. So just wanted to talk about the second. So just 1 second. So the quiz asked you to solve the problem of finding these what are called supports. So if you remember, there was a problem that you're given a directed acyclic graph, and you said that a vertex UV is a support. So vertex V is a support if for every vertex, so this is V, if for every other vertex, either the vertex has a path or this has a path to that vertex, okay? But it's possible that this might have paths to some of them and it may have paths from some of them. So an example that was given was if you have these three vertices, everything here is a support. This is a support because both of these have paths to this. This is a support because one of the vertices has a path to it and the other vertex has a path from it. This is a support because it has a path to everything. Okay. So I think a lot of you got the understanding of the problem, correct? The second question was on finding all the supports of a DAG. Okay? And one way to do it is certainly check for every vertex whether it's a support. How can you check whether a vertex is a support? Well, you run a DFS or whatever you want to run from that vertex so that you figure out everything it reaches. You reverse the edges and you find out everything that can reach it, and you check to see whether it includes all the vertices. If it does, then that is a support. Okay? So you could do this for every vertex. So that's like 2 DFSs, that is n plus m, but you could do this for every vertex, and that would be n times n plus m. Okay? But that's not the best way to do it. The best way to do it is something very similar to one of the problems you solved in a problem set. So what is happening if you were to run a topological sort on the DAG, what does the situation look like? For a vertex to be a support, it has to be able to reach some vertices, and others have to be able to reach there. So the picture should look roughly like this. Okay? Of course, it could also look like this. So then these are all vertices of support. Okay? Things here will not be supports because there will be something else that doesn't have paths to this. And similarly, things here may not have support to things else. So what you need to do is you would follow the algorithm like in topological sort, but whenever you find that there is only one source as you're going across, at any point if you find that there is only one source there, then this vertex has a path from everybody and it has a path to everybody. Okay? If ever you find that there is a multiple sources, and the other thing to say, if ever you find a vertex that's a sink, and then there is also a source left, then there will be no supports because the sink cannot reach any of the source and the source cannot reach any of the sinks. Okay? So the main thing to do was to do just like you do in topological sort, and then check this condition and return the rest of the. I'll post the solutions. So let me